So good morning, everybody, and welcome to the 225th Earth to Class program. As we always say, it seemed like a good idea at the time. So let me give you a brief introduction to volcanoes. This is a modification of a slideshow that I used previously, but not for about 5 years. We're talking about volcanoes. What are they and how powerful are they? And recent activity around the world raises interest in volcanic activity. The Lamont campus itself sits on top of what can be considered a volcanic site. It's the Palisade Sill, which is the remnants of igneous activity about 195 million years ago. And in the New York, New Jersey area, we have other igneous features, including the Watchungs, which are hills near Paterson, New Jersey. And in the Connecticut River Valley is a series of basalts also formed by volcanic activity. Most of the time we're aware of continental volcanoes, but of course most crustal lava forms the ocean floors. The mid-ocean ridge system consists of basaltic flows with islands rising above the sea surface in various locations. Scattered across the ocean basins, especially in the Pacific, are hundreds of seamounts and geos. So this is one map showing the ocean floors. And the discovery of the mid-ocean ridge was one of the important things involved in understanding plate tectonics. During World War II, Lieutenant Harry Hess in the US Navy, who in civilian life was Professor Harry Hess at Princeton, was involved in transporting goods around the Pacific and using some of this newfangled sonar stuff. He discovered these flat-top seamounts. He named them geos after the Princeton Geology Building. Professor Geo was the first geologist at Princeton. This is a image showing what a geo looks like, flat top seamount. And modern technologies like side scan sonars have allowed us to create details of the ocean floor. This is part of the East Pacific Rise, some of the nearby seamounts. In 1977, an amazing discovery was made of black smokers, which are hydrothermal vents rich in sulfur minerals. The research submarine Alvin accidentally discovered these, realized the material is coming up out of the ocean floor in various places, which are mineral rich. And these, back in the past, have led to some amazingly rich ore deposits. It's thought that some of the big ore deposits that we had in New Jersey, in the Franklin area, possibly were created by black smokers in the Precambrian times. So this is a diagram that represents what happens when volcanoes erupt. Magma rises, can stall and stretch out to become sills or dikes. When it reaches the surface, it can explode, producing tephra, which is rocks, gas, and ashes, or lava flows. Volcanic gases mix with the atmosphere, which can have impacts on the climate. The Hawaiian Islands are some of the largest volcanoes on Earth. And this is one image which shows many of the volcanic islands of Hawaii. Jim, which ones have you visited? You're muted, Jim.
I'm sorry. Mauna Kea and Mauna Loa. Keck Observatory is on top of Mauna Kea. And the view up there at sundown is just amazing. I've sent you some of the photos I've taken there. It's just breathtaking. We were on a cruise to the Hawaiian Islands in November. And 2 days after we pulled out of Hilo, Mauna Loa decided to wake up after 30 years. And I think I sent you those pictures as well.
Right.
Just amazing. Absolutely amazing.
I'll get some of them up on the Earth to Class website soon.
Okay.
Anybody else have personal experience with volcanoes?
My husband was there when Pinatubo erupted. He was in the Philippines.
Mm.
And he didn't take you?
No, he was young. I didn't know him yet. But yeah, he escaped. He was actually living there when it erupted.
Okay, thanks. Okay, another type of volcano, which is what most of us think of as volcanoes, are called stratovolcanoes or composite volcanoes, which consist of andesite and other lavas. They're cooler and more viscous than basalts, and they're intermingled with pyroclastic materials. These are the sorts that we see in many places. If some of you have ever traveled to Seattle, it's amazing. The plane may still be above the level of the clouds.
Mhm.
Poking up through the clouds, you can see Mount Hood and several of the other volcanoes of that range. Third type of volcano is built of cinders and ash. One of the most famous is Paracutin. A farmer was working in his field in 1943, growing corn, when the ground began to shake and material started to come up. By the time it finished, it was about, I think, 1,500 meters high and spread out over many square kilometers or hectares. Another feature we have from igneous activity are called flood basalts. At times in the Earth's past, we've had vast amounts of lava spewed out onto the surface, covering thousands of square kilometers. In the United States, the Columbia flood basalt in the Pacific Northwest is the US largest. Much of the Deccan Peninsula in India consists of flood basalts. Another feature we see in volcanic activity is called columnar jointing. And we have it in eroded features out in the American West. I think in the lower left, we have something called the Devil's Steps, which I believe are in Ireland.
Yes.
And then we have the Palisades. Lamont is to the right in here. This shows one of the landslides that took place back in, I think, the 1980s. And one day, just a whole bunch of material came down, destroying some of the buildings underneath it. There are various places where you can find out a lot more about volcanoes. I'll put them onto the website. But by recent estimates, there's 169 active volcanoes in the US, mostly in Alaska and Hawaii, and about 1,500 or so potentially active worldwide, not counting undersea volcanoes, with about 500 definitely active in the last 100 years. Southernmost volcano is Mount Erebus in Antarctica. And we have volcanoes in the north of the world, on the Gacko Ridge in the Arctic Ocean.
Mm.
In 2001, we had an expedition called the Amory Arctic Mid-Ocean Ridge Expedition, which featured in detail about 1,000 kilometers of the Gacko Ridge. And the Smithsonian Institute has a volcano website. It's Global Volcanism Program, which is a place where students can get information about volcanoes. They have weekly reports that look like this. One of the obvious things we know is that we have a connection between volcanoes and earthquakes. This was some of the critical information that was used to map out the mid-ocean ridge in detail and understand the idea of plate tectonics. Another type of feature we have are called hotspots. These are places where volcanic material is rising up. One of the largest hotspots in the United States is in Yellowstone, which had a massive eruption several hundred years ago and could erupt again. The Hawaiian Islands are located over a hotspot. We have a plume that periodically sends information up or sends lava up, create new islands. And then as the plate moves, a different area will be over the hotspot. Iceland is also on a hotspot. By studying the islands that have formed over the hotspot of Hawaii, we can also see that they extend to the northwest. They form the Midway Islands, which were very important during World War II, and the Emperor Seamounts up here.
Mm.
Iceland is among the most active regions in the world. I had the opportunity to go to Iceland a few years ago. You can stand right on the rift and get a sense of what's involved as the Atlantic Ocean continues to widen.
Mm-hmm.
This geologic map showing some of the volcanoes of Iceland. Eruption styles of volcanoes differ. Sometimes we have lots of smoke coming out. Sometimes it's just lava. Sometimes it's in between. The gases that come out of volcanoes include water, carbon dioxide, and sulfur dioxide, with lesser amounts of carbon monoxide, hydrogen sulfide, COS, CS2, HCl, hydrogen, methane, HF, HB, mercury, organics, and gold. Trace amounts of selenium, cadmium, bismuth, lead, etc. The tectonic setting affects gas composition. And we can do both direct sampling of volcanoes, which Jim has done, and remote sensing. Jim, you want to talk a little bit about the direct sensing you did?
Well, it all started when we visited Shishol in the Aleutians. And because of my knowledge of mass spectroscopy, we actually sampled some of the gases coming out of the crater. And that's been my specialty, sampling volcanic gases. Because when I worked for Pepsi and Seagram, I was a senior research chemist, and that's the instruments I used. And anytime I have visited a volcano, it's been with friends I made or acquaintances I made at some of my other trips. And it is very impressive to see these things go off. It's kind of, you wear a mask because the sulfur dioxide and some of the other sulfur materials are just not good to breathe. But then when you realize what you've just walked on and sampled, it certainly gives you things to talk about with your friends.
This is one of the outgrowths of Earth to Class. I took Jim and a few other teachers to an AGU conference.
And that's how I met these people. Yeah.
So you never know what happens when you meet me.
Yeah. You find friends that are trying to kill you.
So some of the volcano hazards are lava flows, the ash or tephra, lahars, which is a water and solid flood, volcanic gases, pyroclastic flows, which are very hot and very fast moving material coming down the slopes, landslides, and of course they can blast you into tiny pieces if you're too close.
Would you believe people try to take selfies with the lava coming out of the Mauna Loa eruption back in November?
Yep.
I think crazy. Well, yeah, they are.
One of the most famous eruptions took place on the Caribbean island of Martinique,
Oh, yeah.
which was very, very populous before. And then one day in 1902,
That's gone.
the volcano Pele erupted and
Yeah.
destroyed the entire town. The story is that there was only one person who survived, a guy who was locked in a subsurface jail. And the lava went over the jail, destroying the building, but he survived. They found him afterwards. So one of the things that some of the Lamont scientists and others work on is preparedness, identifying the hazard zones, creating emergency plans and kits during and after an eruption. Iceland has done a tremendous amount to try to prepare the population for when volcanoes erupt. I've got some links to that in here. And the final point I want to make is that volcanoes also have global climate impacts.
Oh, yeah.
It's neither the cause of climate change nor the solution. But by putting a lot of materials into the atmosphere, sunlight can be reflected back out to space, causing climate cooling. And some of the gases also affect the ozone layer. May have some impact on El Nino. So I'm going to stop my screen now. I get spam messages about every 5 minutes. Sorry if that showed up on the recording. Okay, let me get this out.
Okay. I share my screen.
Susanna, you want to put your screen up now?
Yeah, I have it on. You see my screen?
Yes.
Okay, thanks for this. It was a great introduction. We talk about now about certain aspects of this, which are part of our project in the Aleutian Arcs. First, I want to reintroduce a parameter I use a lot in today's talk, and this is the volcanic explosivity index. This was an index that was introduced in order to have a means of describing the magnitude of an eruption. Just what Mike talked about, right? This Paricutin, that was a very small eruption, maybe in the explosivity in the index here, maybe about 1. And of course, we have then much bigger eruptions. You see the Mount St. Helens eruptions at is about between 4 and 5, straddling The Pinatubo goes and presses towards 6, and we have still much larger eruption here, the Yellowstone caldera. That is is a so-called super eruption. And it's two things that are important for us. This index is based on the total of erupted volume, and that was the one thing, and it's a logarithmic scale. So between the scales, it always goes up by 1 magnitude. It's just based on that. Somebody goes out, measures in the field what on lava and tephra, the effusive flow and the broken volcanic rock have been measured the total volume, and tries to see where on the scale we are. It's a useful means in comparison. And just to give you a couple of examples, in the recent years, there were eruptions that can be classified by that index. You will remember the 2010 eruption of this little Icelandic volcano. It had only an index of about 4, but you will remember the chaos it caused, the many flights that was canceled, stranded millions of passengers, and was a big economic loss for the airlines. Only 2 years ago, the Camprovea eruption on La Palma Island in the Atlantic Oceans. You have seen the spectacular pictures, most likely from that, what caused. I have visited La Palma myself many years ago. It's a beautiful island. And it's a shame to see how much destruction this very small, this rather little small eruption has caused. Millions of nearly $1 billion in damages, thousands of homes destroyed, people displaced. It's that what happens right now if a volcano erupts in a fairly well-populated area. And about 1 year ago, we had some more spectacular explosive eruption in the remote island of Tonga in the Southwest Pacific, the Hunga-Tonga eruptions, which came on very suddenly. It was known that this volcano was active, no significant danger was perceived, and then we suddenly have an eruption like in about the size of Mount St. Helens. The death toll, only 3 people, which was fortunately not a lot given the size of the eruption. And of course, despite being a remote place, it's a huge economic damage. But we need to keep in mind that these eruptions, as spectacular and dangerous they are only peanuts compared to certain major eruptions in the geological past. My first introduction, I just recall a couple of the examples I mentioned back then. We have really famous Krakatoa eruption in 1883 in the magnitude of 6. It's famous for the tsunamis that was associated with this. You see the volcano Krakatoa is located in the Sunda Strait between 2 major Indonesian islands, Sumatra and Java. So this explosion caused a tsunami, and that killed over 30,000 people in the surrounding island of Indonesia. It did affect the temperature. The global temperature perceptibly went down, and the spectacular and the dust it ejected into the atmosphere caused the spectacular optical effects and beautiful sunsets for many years that were well kept by the contemporary painters. And that's way 6. So we have global effects already, severe loss of life. Another one that's very famous is the Tambora eruption of 1815. I mean, that's about 200 years ago only. And it's connected with a year without summer in 1816, and the after effects of this eruption. We had snow and frost in New England in June. There were crop failures, famine worldwide, diseases, major loss of life. Let's see, still the site of the caldera. It must be a beautiful place now, hopefully dormant. In the deeper geological past, in the prehistoric past, 75,000 years ago, we had a geological super eruption. And of course, it was not observed, but the question is, was this a global ecological disaster? It was followed of perhaps of 10 years of volcanic winters and a long extended period and human life scale on cooling. This is just a couple of examples, and of course we are interested how often such eruption takes place in the geological time. And we need to know this for one very obvious problem is a hazard posed to human life and habitat. They are destructive, these eruptions are incredibly destructive, they are sudden. And you must remember, we have no means of preventing this. We can only mitigate the consequences. And also on the actual side, what Western say do have climate effects on the short scale. We know that volcanoes have this, but do they have accumulated climate effects potentially that are a climate player in the climate change that is now taking, that they are a player in the climate change that is now taking place. So in order to see what the geological past had in this eruption, we need a record. And this has always been a bit of a problem because I mentioned this last time too, because on land, we are not going to find this record because, you know, volcanoes are loose, often of loose material, the pyroclastic material, the volcanic lastics, they erode very quickly. It's incredibly how fast this goes at an eruption, that this loose volcanic gravel is eroded away. The building itself are unstable, and in geological time, they go down really quickly. And anyway, we don't record on land. So our remedy is going to the sea. Up there is a sketch of a volcanic eruption as an explosive when we have a major explosive eruption, there is a plume that goes into the atmosphere that's drifted around by the wind. And then we have ashes that fall out and form ash beds in the ocean. And as you well know, in the ocean, we have a sedimentary record, one layer builds after the other. That gives us a very good temporal sequence, and that's why we go out on drill ships in the sea, drill the sediments, and to see what's happened back in time. And as ash layers are embedded in the sediment, we get the records of past eruptions. You see on the right side, there is an example of such an ash layer about 5 centimeters thick, very typical, with a sharp basis, you can still see, and then a little bit grading here on the top, because when the volcano happened, it's a geological instantaneous event. You get a lot of ash that goes into the ocean, falls in, and then it sort of tapers out. It's very characteristic. And also these ashes in the single core is only a 5 centimeter. Because these ash fans are so wide distributed, here on this map there is isopach from this V6 Tambora 1815 eruption that were done in the Java Sea after the eruption. And you see it goes 100 kilometers away, that we have the isopach of 5 centimeters, there are 100 of square kilometers involved, and this by itself, by this this spread, it contains a considerable amount of volume. So we can measure this volume and we can date this ash in the sediment, and then we know when an old eruption has happened and can estimate about the volume and from the volumes then again about the eruptive magnitude. And going back to climate, this is a very famous paper from Kenneth and Tunnell that was published in the 1970s, almost 50 years ago. And this was a compilation of those ash layers as they have first been drilled in the deep sea drilling project. And here we see they just counted it per time, per million years. So the million years go back till 20. And you see some fluctuations around around the Miocene time, more than 10 million years ago. But what was most significant was really, and that was well documented, an increase at around a little bit before 200 million years ago, since these ash layers simply strongly increased. And that was at the same point when the onset of the glacial cycles on Earth occurred, when Earth became so cool that we went into a period where we had consistently glacial times. This connection was recognized since then and was confirmed actually in many, many later studies. And as the drilling crews went in the 1990s to the Kamchatka Aleutian Arc, and you see these black dots. These are several drill sites that was done on this expedition, started from 80, 81, 82, 83, 84, and then here over here at 87. And they found amazingly, and all of this drill site close to the Kamchatka Arc, the Kurils and the Aleutian, all volcanically active areas. They found that about 2.6 million years ago, this frequency of these ash layers in the sediment rapidly really increased. And this was about the time when the northern hemisphere became glaciated. So this connection between the increase in volcanism and the global cooling was really confirmed by these more detailed growths that followed about 25 years after the original growth. And in my project, we began to work on this site, rework, I have to say, on the site 882, here close on the close to the intersection between the Kamchatka and the Aleutian Arc. That is here again. Simply because while these early studies were made following this original, following the drilling, they were still very preliminary. For example, they counted the ash layers, but it was never clear when I went back to the record whether it was actually 50 ash layers or it was over 100. Because sometimes the people, we still disagree on what is an ash layer and what is not an ash layer. So my project was about going back to this site, looking on these ash layers, re-recorded. And I will now talk about a little bit results, what we did on this side, 882, and also on the other one, the side 881, with a little bit further to the southwest. I just mentioned that the Kura, the Kamchatka Aleutians, all very volcanically active area. These red triangles these denote the volcanoes. And these circles here, this is an indication of relative eruptive magnitude. The Kamchatka has a larger, is known for having fairly large magnitude eruptions. The corals too, but you should also keep in mind that these white circles are only fairly recent eruptions that are still there in the subaerial record. We just don't know what's really going back deeper into the time. And in going back deeper to the time, we need to go to the drill course, which goes back to about 2.6 million years. So it covers the entire Pleistocene period. And yeah, so that's it. And we addressed so far, I worked on 3 questions. We wanted to know what kind of magnitude an eruption has to have in order to make ash layers, what are the volcanic explosivity indexes. Small eruptions, like, for example, like the Pericodine does not make these ash layers. You have to have at least an eruption like Mount St. Helens in order to produce a marine ash layer. So we know what, but we can get this a little bit closer here. We also wanted to know, volcanoes are associated with certain, we can measure the composition of these eruptions. And we wanted to know whether there is any change in the chemical composition, especially as the frequency changes. And lastly, we were more interested in the question whether the increase in volcanic frequency actually precedes or does it follow the initiation of this glaciation? Because this tells something about the effect and cause, what was first said, the climate change and then the volcanism, or was the volcanism started to go mad and then the climate change happened? So this is important to know the temporal relationship about these 2 things. And the magnitude of the eruptions, there is actually a very simple formula that has been done by experiment and series that was invented about 20 years ago. And we can make a minimum eruption. A minimum volcanic volume, we can determine it from this formula. You see, it's very simple. It just needs the tephra bed thickness, this is T. And the other variable is area over an area which where the tephra was deposited. So if we measure the thickness and make a couple of simple assumptions on this area of that, then we can arrive at a minimum volcanic volume. And this is simply done. We have the site 82 or 881, and we look around where the next volcanic sources are. There is nothing here in the ocean which can produce it, and the closest volcanic sources to site 882 is actually Kamchatka, which is about 700 kilometers away. Or it's possibly the Western Aleutians. We don't know the volcanism here as well because the Western Aleutians are largely submarine volcanoes. But still, this is only the current view, the historic view. We don't know what was here in the geological past. Anyway, and we can also here inside at 881, the minimum eruption. The next possible source is here the Northern Kuriles are. So we make a couple of assumptions. Of course, these green circles, it has to come from here and it's spreading a little bit out and you pull around with the shape. Of course, it's only a minimum because you never know if in eruption, it can go all over the place. But make a minimum and it's a starter. We can play around here with possible area shapes. Ellipse is mostly assumed, so the volcano is on one side and the drill core is on the other side of the length axis. We can also use a sector area shape, assuming that the volcano is in the center of a circle and goes over here and over a sector. which is here intersected by the Chilcoot. It doesn't matter really so much. And once we have this area determined and the minimum volume determined, then we can calculate, use another formula just to calculate, to estimate the minimum eruptive magnitude. And there we are. And this is a fairly simple calculation. Is only in one thing we need to pass check out. Here I made on the left side, I made a thickness distribution from thicknesses of these ash layers as we measured them. You see it goes maximum up to 50 centimeters from a couple of centimeters. This is from slide 881. Of course, the frequency, we confirmed that increases at the Pleistocene-Pliocene boundary, which is about 2.6 million years ago. And you could also say, of course, it's a linear function of thickness, is the eruption magnitude, it's going to increase. But we also need to take into account that during that time, this site was not stationary. I show this on the next slide in a moment. What I mean here, see, it will really matter if you have this, assuming that here on this little cartoon on the right, the low side, that the volcano is here at 0 kilometers, and then there is an exponential decrease in the thickness of the ash layer. And whether you measure it at 560 kilometers, where it could be 55 centimeters thick, or you measure it at 768 kilometers, where it's only 20 centimeters thick. And we have to take this into account because, of course, we have a plate convergence. The Pacific plate is moving towards the Kuril-Kamchatka arc, and the plate is going down here in the trench, and over a period of 4 million years, we are dealing here with, of course, the side moved towards Kamchatka and decreased the distance. And yeah, if I go once back, and you see the closer it is, then eruption that is closer to the arc will measure at a larger thickness. So once we correct for this thickness and calculate from the thickness then, so the explosivity index, you see here in the blue dots, these are the eruptive magnitudes calculated for the site, and the straddle this is about the magnitude I showed in, I hope I'm still here. Oh, yeah. Yeah. I just got a warning, my internet is not working, but I hope I have just yeah. And yeah. And
We're still
there's
hearing
no
you.
really change in the time and in the eruptive magnitude over that. It's really constant. What just changes, and that's indicated in these red layers, is a frequency that sporadically changes, cyclicity in volcanism. But the eruptive magnitude between 5 and 7, it remains about. So we know that in these past 2.6 million years, we had regularly eruption ranging, straddling around 6, which is in the size of these tempora 1815 eruption of the Krakatoa eruption, which are really devastating catastrophes. We also straddle towards size 7, but they are fairly infrequent. And the Russian colleagues are actually working on that. I mean, I showed this, here's again the site 881, and here is a Kuril-Kamchatka arc. They used one tephra layer, which is 50 centimeters thick at the side, and were able to use a composition of these tephra layers and to identify the source actually on the Kamchatka arc, which is a Pautseka caldera, This is an ignimbrite showing the ash deposits just here on this photo, very close to the crater. You see these thick ash piles. And in the Coral, it's part near the Coral Lake area, and about 40,000 something years ago, it exploded. It was a major eruption. It caused a tephra layer 50 centimeters thick in this one core at 81. And over here, it was still measured at 5 centimeters thickness at this side. And they also found these tephra layers here. They were able to make, of course, the more core you have, the better the volume eventually become. And they estimated this size about 7.6. And this was certainly one of the largest eruptions of that area. We don't know still whether we have a magnitude eruption of size 8, but as I have to emphasize that these are only minimum estimates that give an idea what we are dealing with here, but not yet accurate numbers. So it was definitely volcanic active, destructive, lots of destructive volcanism. Eruptions, I hope we do not see today. Anyway, then we continued. That was a question on the volcanic explosivity index of the magnitude of the eruptions through time. Then we looked at the question, sorry, whether we had compositional changes. And what we use for that, we use these ash layers are composed of many of them contain glass shards, which is just a chilled and frozen magma. On Hawaii, you might have seen it. It has often, that the ash has often a very glassy experience, and especially the explosive eruption create a lot of these glass shards, usually thin some, and these glass shards composition is an equivalent of the melt composition that produces eruption. So all what we have to do is to separate these glass shards out. We have often very bubbly shapes and very distinctive, very easy to recognize and to analyze their composition. And that's where I spend a lot of my time on. We have a sample processing, but you see this circle here, this is amount from 1 inch. And we have 12 holes on that, and each hole contains a glass shards of one of these ash layers that has been separated out by wet sieving and freeze drying and mounting anyway, and can then be analyzed by the electron microprobe. This way I was able to analyze very easily well over 150 ash layers. And these are the results. These are 2 chemical variables, SO2 content, which gives us about what these ashes are in terms of how we classify this composition. You see andesite, dacite, and rhyolite. Rhyolite is very silica rich. So most of these ashes are very silica rich. It's very typical for explosive eruptions. And the other important thing is here the potassium on the y-axis. I hope you can see the different colors somehow with these are over 70 tetrabeds, 77 tetrabeds. I'm running out of colors, but they have very distinct potassium ratios, and actually a range from about 0.5 to 4 weight percent potassium is huge, and tells us there are considerably variation in the composition of that. And then we can just look whether these changes are, whether how this goes through times. Yeah, measure also many other elements, but potassium is very indicative of change. And we do not see an overall directional change. We see a lot of fluctuations, that's definitely there. but we do not see any major change. And this is actually it's a significant result, because it means that the volcanic systems that produce these ash layers are the same over the time. They don't really change. And but the only thing what they change at the Pleistocene Pliocene boundary at about 2.6 million years ago, when the ice cycle started, to just get more frequent. And this already points to an external driver. Something forces the system to become more frequently, but it's not something that changes internally within the system, because then we would be seeing a chemical change. So that was no compositional change. Fluctuations, yes, it's significant, and we are still working on the causes, but no singular change in one direction, that it gets more potassic or less potassic or more silica rich. No, it's nothing. It's just always the same fluctuation, and then the change in the frequency. So this was a result, but we still so we have still some very important result pending right now. We want to know whether these eruptions are really coming out from Kamchatka, which is consistent with the wind directions, the stratospheric wind that will drive this ash out to the east into the ocean from the volcanoes and deposited here. But my feeling is we get also something from the Western Aleutian arc, although it does not really look a lot of explosive, but as I say, this is only the most recent one. We don't know what's in the geological past. So I'm still waiting about the result from lead isotope analysis. Lead is a tiny trace element in these ashes, but isotopes will allow us to tell us whether these ashes come really from Kamchatka and or possibly from the Western Aleutians. And then I know that the Russian colleagues are working on making more land to sea correlation, at least for the younger ones. And about 18 months ago, I went into contact with the Russian colleagues, and it was very nice. And they invited me to come to Kamchatka, which I wanted to do very much. But then 11 months ago, the world events interfered with this plan. So right now, it's a little bit sad, because it would have been nice actually to be in direct contact with the people who know so much about Kamchatka. So, and then the last question I wanted, we are working on whether the volcanic, this increase in the volcanic frequency, here seeing now for site 882 and for site 881. The site 881 has a couple of more tephras, but we see also here the site 882. You should also watch here for the thickness. It's at a different scale. The site 881 has about 50 centimeters thickness. The site 882, the maximum thickness is about still 19 centimeters here in the early Pleistocene. But anyway, both sides have this increase in the frequency at about 2.6 million years. But meanwhile, we had better investigations, and we see the signal in the sediment on the initiation of the Northern Hemisphere glaciation started slightly earlier. And by redoing the timescale, this was also a big part of the project, trying to get the best possible dating of all these tephra layers to see when they really started. And we can right now say confidentially that this initiation of the Northern Hemisphere glaciation started before the increase of this. This simply means that the frequency change in volcanism is driven by the climate change, because the climate change the glaciation comes first, and then the increase in the volcanism comes later, or this indicates us again that possibly the climate change is the driving force. A question I have here is these black wiggly curves in the Z. These are orbital cycle signals. This is going to be my last slide. You see these ashes are sort of cyclic. They are not really coming regular. We don't know really the reasons for that. Sometimes if the wind just blows in the wrong direction towards an eruption, there will be no ash layers. But it has been long a question whether the cyclicity in the tephra might have to do something with the orbital signals that are hidden in the sediment. So this black wiggly curve is a delta O18 signals from benthic foraminifera, small organisms that live on the seafloor. And if we measure the delta O18 in them, it gives us that curve, and it's well known that these curves, that this cyclicity of the black curves relates to the Milankovitch cycles, which describes the movement of the Earth relative to the Sun in various parameters and the eccentricity, obliquity, and precessions. And there's always been a question whether this, perhaps one of these parameters also shows in the tephras. I talked to a couple of experts, and they say okay, there are not that many tephra beds, with about 77, but we might be able to see something in the eccentricity. So I took up with, gave this to an expert. I'm not an expert in making these time series or spectral analysis, as they call it. And perhaps Brendan Ray is going to tell me something once I'm back from New Zealand, back in New York. So to wrap this up on this question we have addressed so far, what's the magnitude of these eruptions, of these past eruptions are in the past 2.6 million years. It's easily 6 on average. Some sizes of 7 are likely. So we know these are really major catastrophic eruption. If we had one today, there would be major consequences for whatever population it is, and we would feel likely also global consequences. We would feel a slight climate change, a cooling for a change, not a heating. We have no changes in the chemical composition as the frequency increases, so the volcanic systems remain the same. And finally, we find again evidence that the increase in volcanic frequency follows the climate change. And this is actually telling us that the climate change is likely driving that volcanism. I think this is actually awesome. If you imagine volcanic eruptions are so huge, they are absolutely impressive, but they do not drive really climate in the long range. On the other hand, we have this really powerful climate system in the ocean current and in the atmosphere, and if we have changes there, they can even affect the volcanism. So this is also underlying the power of the climate system. So I stop here and thank you very much for the attention. I hope I can take questions despite my not so great videos and acoustic once more.
Thank you very much, Susanne. I especially enjoyed your anticipating my question about Milankovitch cycles and volcanoes.
Yeah, I hope Brendan is having, I just gave him my data before I left, is going still to have a couple of answers whether we can see them. And it's just not so easy to find a good core, we need a good core we can date that has plenty of tephras. and this is not interrupted by drilling, and we don't have so many of this. We are still looking for better ones. So, but I hope one day we will be answer that question.
I was thinking back to when we were looking for answers to individual parts like the Milankovitch cycles. And now we're combining it with many other things. Okay, questions from other people.
Okay, you're gonna have to forgive me as a chemist. Here goes. The dissolved gases in that ash probably lower the pH of the ocean water initially. Yes?
The gases, when I showed the glass shots, I have plenty of bubbles. And these bubbles tell us actually the gases went out during the eruption. So once the gases goes into the sea and stays there for a long time, they start to decay, but usually this changes on the microscale. So it's actually volcanic gases that go into the atmosphere where they cause affect the climate. There is not too much left. These glass shots are degassed. Sometimes they have a little bit of water still left. This is residual, but they don't go so much into the sediment.
Next question. The minerals that are mostly metallic minerals that are in the ash, when they do sink to the ocean floor, they will probably promote growth of the microflora, which in turn will help the food chain. Could that explain why some of the West Coast fishing fleets go up by the Aleutians, where it is just rich in sea life?
Yeah, it has long been speculated that these ashes biofertilize the ocean.
Yeah.
But we are still not sure about these effect relative to that what the ocean system by itself does by the ocean current. And it's generally believed right now still that the ocean system itself, it's more important in fertilizing the ocean than the ash that is brought in.
Sure.
But this is another major research question. People are still trying to understand how quickly these gases dissolve, what especially in iron or phosphorus would be getting into the ocean,
iron.
Whether they cause a short-term bloom. I mean, we are rarely around when this thing has happened, you know, and the historical timescales go out after such an eruption into the sea. I think it happened after the Pinatubo 1991 eruption. This kind of investigations were made, but it's still inconclusive how strong these effects are.
Okay. Thank you.
Yeah.
Other questions? Okay. If we don't have any other questions, we have a nice day to get out to. Everybody can go romp in the 40-degree weather. Okay, next month, on the 25th of February, we have Ajit Subramanian talking again about some of his microbiology. And then on March 11th, we have Michael Praviti, who's been with us once. Mike's going to talk about the Arctic amplification and some climate stuff. So I look forward to seeing you all at future Earth to Class programs. Just a reminder, this was number 225.
Wow.
So as we say, it seemed like a good idea at the time.
Yeah, right.
It's all Christiana's fault.
That's it.
She got things started. Forced me to go away from my safe little transparencies. Okay, stay well, everybody. Suzanne, thank you once again for joining us.
Yeah.
I hope you have.
Thank you for being there. Yeah. Bye-bye. Have a great day.
Bye.
Have a good weekend.
Bye.
Okay, bye, everybody.